Hi. Ready, set, go. Okay, so we're still talking about simple harmonic motion, pendulums and springs. I kept these two formulas from last lesson. They're really, really important. For a spring, acceleration will be k over m times displacement. Technically, it's negative, it's reverse. And for a pendulum, same thing. A is g over l times displacement. Technically negative. Conceptually, it's important because the farther you are from the center, the more acceleration there is back to the center. But we're going to use this a little more calculationally today. So last lesson there's a video where a circular motion is related to a pendulum. Circular motion also relates pretty well to a mass on a spring. So let's do that. Let's imagine an object is going in circular motion. Let's say it starts here and rotates counterclockwise. So theta goes from 0 to pi over 2, pi, 3 pi over 2, 2 pi. Remember, we're in radians, not degrees. So that's going back and forth. In theory, the motion of this object in a circle will exactly match a mass on a spring. The mass starts here. Let's say this is a block and a ball. If the ball starts here and the block starts here, and by the time the ball reaches here, the block will be here. That kind of is a spring. And then when the ball reaches here, the block will be here. And as the ball goes back and forth, back and forth, back and forth, the block will also go back and forth, back and forth, back and forth, back and forth. Okay, don't keep. The mass is here. It goes up and down, up and down. So the ball goes up, down, down, up, down, up, down. In theory, this will exactly match the motion of the spring, up and down, up and down, up and down, bouncing up and down on the spring. Since they match, we can make an equation for the position of the block. Let's say this is 0. And let's say upward is positive, downward is negative. What kind of function with respect to time will give us a function for the height or position of this block? It is sine. Yeah. If we take the sine of the time, we'll get something that at least matches in shape to the location of the mass on the spring. I'll explain this in class if confused. Please don't hesitate to ask questions. D versus T for a mass on a spring will look something like this. It will make a cyclical sine curve over time. Two minor things. Does every single spring in the whole world always go from 1 to -1 meters? No. They all have different amplitudes. So if D is not equal to sine of something, it's equal to the amplitude times the sine of something. When sine of whatever is 1, then we're at the amplitude. When sine of whatever is -1, we're at the negative amplitude, the other direction. When sine of whatever is 0, displacement 0. That would be when it's at the equilibrium point, which is good. Great. Perfect. So that's cool. there's one more trick. We can't take the sine of a time. This is theta. We can take the sine of a theta. That makes sense. See this? In case it wasn't clear earlier, the height of the ball is sine theta. And that makes sense because that's the height of the spring also, hopefully. So we need a constant to multiply by time. It turns the time into an angle theta. It's a curvy W. It's not a but. It's a curvy W and omega. And omega t equals theta. This is pretty nice because we can come up with something cool. What's theta for a full circle? Oh, my baby's telling me it's 2 pi. And what's t for a full cycle? Not circle, cycle. A period. We're going to use period again, like we did way back in circular motion. Period for a cycle is capital T, not little t. So omega can be expressed as 2 pi over t. And it can also be expressed other ways, which are going to be just good times for everyone. Just a fun time all around. Very exciting. Okay. Alright, let's find V. V is also going to be a sine function, a trig function. It's not going to be sine, it's going to be cosine. If you know calculus, that's obvious to you. If you don't, it's okay. We don't really care about that. Let's find V max. If you are curious, okay, if you do care, is something cosine. Okay. Just like the maximum amplitude, no, the maximum displacement is A amplitude, and the displacement is amplitude sine omega t. The maximum velocity is V max, and the velocity at any time is V max times the sine function, because just like position goes up and down, the speed of an object in SHM, superharmonic motion, also goes up and down. What is V max? We could do it with calculus, but we can also do it with something else. So masses on springs and pendulums swinging back and forth. Do you remember the other method we could use to find V? We can find K and find V. The energy is 1/2 mv squared plus 1/2 kx squared. If it all becomes kinetic, then all potential, or vice versa, these two are equal. So V max is x root k over m. Looks kind of familiar. Instead of x, I'm going to write d for, again, the displacement of this mass on the spring, because it's in the y direction, not the x. So that makes no sense. Okay. There's another super cool thing that we can do. Another way to find V max is analyze this circle. The mass isn't really going in a circle, it's going up and down. But it does travel the same distance, up and down, up and down. This distance, the diameter of the circle, and back in the same time, t, the period. So another way to describe Vmax is, well, when is this object moving the fastest? Look at the ball. When's the ball moving the fastest up and down? Whenever the ball is going fastest up and down, that's when the block is moving fastest. Because remember, in this hypothetical scenario, which pretend it works, the ball and the block, their motion is synchronized. So the ball goes up, 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 stops here, down, 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 stops here, goes up, down, up, down, up, down. The ball's always going the same speed, but it's going the fastest up over here, and going the fastest down over here. Let me show you again. Look at my marker. My marker is always going the same speed, but it's going the fastest up now, and it's going the fastest down now. Fastest up, fastest down. So the fastest speed up and the fastest speed down are the same. It's basically the same as the speed of the ball all the time. And it's basically the same max speed as the spring. The speed of the spring is the speed of the ball. The speed of the ball is 2 pi r over t. Oh no, I forgot to write the r. On purpose, mind blown, because the r is the amplitude. Remember, amplitude is the maximum displacement. Wait a second. Hold on. Just a minute. Oh my gosh. Totally not planned. Who could have seen this coming? Vmax is, wow. Great job, babe. Thanks. Okay, so you can solve for energy or by analyzing the circle. Same answer. This means sorry, my mistake. If we look at Vmax, it depends on D. When V is max, obviously we need to use Dmax. What's Dmax? Dmax is a. I'll do this again in class if you're confused. I apologize. Oh, wait a second. Oh my gosh. We made an incredible discovery. That's also on the reference table and has been for the whole year. Omega is root k over m. And I could have done the same thing for a pendulum if I felt like it. Trust me. Omega equals root g over L. And omega is this. I know it's a lot of math. I'll leave this video up. I'll talk about it in class. We'll spend some time on this to make sure we all get there. But we figured out, we defined omega and found the formulas for omega just now. Amazing. Good job. Perfect.
you gonna do it?
It's close.
Tipped it. It's touching it. It's touching it.
Oh.
At least it's made contact. Yeah.